going to demonstrate how to solve Newton's laws problems using the free body diagram method. Here we have a situation where we have a box of mass m hanging from a wire that is suspended from an immovable object like the ceiling. So we might very well want to find out what is the tension in this particular string that's supporting the mass. What we do is we represent any object in the system by a free body, a dot. So we're going to represent that mass as a dot, and then we're going to apply force vectors to it. Force vectors typically appear in the diagram as well. Like for example here we would see the piece of string, so therefore we might have a tension in that string, and that tension on the box is pulling upward. So we're going to label that T. And then there's also force vectors that don't appear in the actual diagram. Here, gravity. We're going to assume gravity is pulling downward on this box, that we're doing this near the surface of the Earth. And so we would have a downward force due to gravity. And the gravitational force on an object is its weight. We call it weight, and it is typically represented mg. So, step one is to take the diagram and convert the diagram into a free body. That is what we would normally do. And we draw a new free body diagram for each mass or junction in the problem. So if the problem had more than one component to it, we would end up with more than one free body diagram. So that would be step one, is to create our free body. Step two is to take this free body diagram and represent this using Newton's second law. Newton's second law tells us that the sum of the force vectors on an object is equal to mass times acceleration. Here, under the sum, it means add up all the force vectors that are acting on my object. So I look at my free body diagram and I look how many arrows are coming out of my dot. If I've drawn my free body diagram correctly, the rest of the problem will follow mathematically from it. So here I've represented this with two vectors, so I should end up with two terms in my sum of forces. I'm going to call upward forces as positive, so this would be plus T minus mg, because I'm going to represent downward direction as negative. And this is going to equal m times the acceleration in the y direction. These are vectors, so I have to add them up as vectors. Here I have only vectors pointed in the y direction, so this is really sum of the forces in the y direction is what I've executed. Since the sum of the forces in the x direction in this problem are 0, it doesn't really matter. Here I'm going to solve now, and I'm going to say T minus mg is equal to the mass times the acceleration. This system is in a static situation. It's in equilibrium, not moving, whatever you want to call it. So its acceleration is 0. So that means that T is equal to mg, which makes sense. That's what we were expecting, that the tension in the string is equal to the weight of the box. This is the simplest possible case, and we'll see how this gets more complicated when we add additional pieces to the system, but the process is exactly the same. So step 2 here was to write Newton's second law for our system. So that was 2, and then 3 is solve mathematically. So we'll see this again on the next example. Here we have an example where we've added an additional mass to be suspended from below mass 1. So the problem is going to be similar to what we were doing before, static, no acceleration involved, and we'll follow the same process. So if you remember, step 1 was to draw the free bodies. So we're going to go ahead and do that. I have to represent each mass in the system by a free body diagram. I have two masses, therefore I'm going to have two free body diagrams. So the first one is going to represent mass 1, and the second one is going to represent mass 2. And you only think about that mass while you're working on it. So for mass 1, I see that there's a string pointed upward, which I'm going to call tension T1, and there's a string pulling downward, so there's going to be a tension T2, and there's the weight of the first object, so there's also a downward force due to gravity, which I will represent as m1g. So I have a total of 3 vectors in this particular problem. On mass 2, I see a tension pulling upward, and this tension, this string right here, is T2 in our diagram, and you'll notice that it points downward on M1, but it's pulling upward on M2. The other force is downward, M2G. So there are my two free body diagrams. Now, step 2 is to use sum of the forces equal to MA. Again, we only have motion in the, or forces in vectors in the y direction, so we can write down just force equations in scalar form. We'll see one later when we have to actually deal with the vector components. So I'm going to write down sum of the forces equals M1A, and you'll notice that this is M1, so M1 appears in the force equation. I have three vectors in this diagram, so I should have three terms in my force. T1 minus M1G minus T2 equals M1A. We know that's equal to 0, so I have the equation T1 minus M1G minus T2 equals 0. So here I have two unknowns, tension 1 and tension 2, assuming we were given the masses. This diagram, I have two forces, so I'm going to end up with doing sum of the forces equals M2A, and you'll notice that that's because I'm applying it to mass 2. So I have T2 minus M2G has to equal 0. Therefore, T2, if I solve, which is step 3, solve, T2 is going to equal M2G. I can now substitute in here, and I could get T1 is equal to, actually I'll go ahead and do the substitution, minus M1G minus M2G equals 0, leading us to T1 is equal to M1 plus M2G, which also kind of makes sense. This top string here, this top string is in fact supporting the weight of both of those objects, so the force on it should be the sum of their masses times gravity. Here we will deal with an object that is not restricted to only vertical components. In this case, we have two wires hanging from the ceiling that come together in a knot, and then from that location is a suspended mass. We'll do the same thing. We'll try to find the tensions in the string. Now you'll notice that there are actually three strings here. It may look like one string. Even if we started with taking one string that's tied to the ceiling, they actually, when they come together, like at this location here in the center, this makes different tensions in the three strings. So I'm going to label them in my diagram so that I can keep track of what my tensions are. I'm now going to do step 1, which is free body. I have two free bodies that I need to draw. I need to draw the sum of the forces on that dot. So I have that T1 or T2 points this way, T1 points this way, and T3 points this way at the junction. And I need to make sure I keep my geometry right. So this angle must be 80 degrees, and this angle must be 20 degrees. And I got both of those angles from the geometry of the actual diagram as presented. And I also have the free body for mass M. And here, again, like we've done before, tension 3 points upward and mg points downward. I can now write down the equations for motion, or the Newton's laws. So I do Newton 2, sum of the forces. So the sum of the forces on that dot have to equal 0 because there's no mass there. So I have T1 vector plus T2 vector plus T3 vector has to add up to 0. Now, these no longer point in one direction, so I'm going to have to deal with adding the vectors. And we know that adding vectors requires components. So I'm going to have to break these into components. So I'm going to look at this as the sum of the forces in the x direction and the sum of the forces in the y direction. So this one problem, this one free body diagram, splits into two pieces. So let's go ahead and do some of the forces in the x direction. That means that there's going to be a component of T1. If I were to pull it out of the diagram and blow it up a little bit, T1 points this way at an angle of 20 degrees above the horizontal. So that means there's going to be a component of T1 pointed in the x direction, which I'll call T1x, and there's going to be a component of T1 in the y direction, which we will call T1y. So T1x is going to equal, well, that's the near side of my triangle, so this should be T1 cosine 20 degrees. And T1y, which is the vertical side opposite of my angle, that's going to involve sine. It's going to be T1 sine 30 degrees. 20 degrees, sorry. Okay, I can